So I was going to say that my presentation has been divided in 4 blocks. First, I would like to introduce myself and my company, because I'm sure that most of you don't know me. Then I would like to talk about the application of the photocatalysis and its main challenges, for moving to showing you some examples of LED photoreactors and some results obtained with one of these reactors in comparison with a traditional mercury lamp. Finally, I will summarize the main conclusions of the presentation. Okay, so like all of you, I did my PhD in the field of advanced oxidation processes. Particularly, I did my thesis in the progress and challenges in the photocatalytic removal of emerging contaminants at the University of Cantabria, Spain, under the supervision of Professor Inmaculada Ortiz and María José Rivero. I also did 2 research stays. That is something and I want to encourage you to do. If you have the chance, you have to do research stays. It's really important. I did 2, one at the University of Cincinnati and another one at Loughborough University. After I finished my PhD, I joined to the company Apria System as a sales engineer. I changed a little bit my working area. What we do in our company? Well, we are a technological-based company, and we aim to offer innovative solutions to our clients in order to fulfill the environmental regulations. We were founded in 2006 as a spin-off of the University of Cantabria, so our beginning was founded in research. And that's why we have highly specialized human resource. We are 11 employees, but 8 out of the 11 we have a PhD in chemical engineering. Where can you find us, in case you are interested? We are located in the north of Spain, in Santander. And what we do? Okay, we have 3 main working fields: products, services, and research and development actions. In products, we offer equipment for the separation and purification of streams, mainly liquid streams, so we work a lot with wastewater treatment, but we also have equipment for gas phase. Our equipment are based either on membrane technology or in advanced oxidation processes. In services, we have consultancy and engineering services, and I would like to highlight that we also participate in research and development projects, regional projects, national projects, and European projects. But why I'm here? Because during the last years, we have specialized in the development of photocatalytic LED reactor. As you know, increasing water demand and shortage of available water are growing concerns for our society. So wastewater treatment appears as a promising solution for obtaining a new source of water. Development of low-cost and efficient sustainable technologies is essential for the same, so several technologies have been studied during the last year, and photocatalysis appears as a promising option. It is a good technology for the removal of emerging compounds because they are recalcitrant to traditional treatment. In the emerging contaminants, we can find pharmaceutical, endocrine disrupting compounds, surfactant, pesticides, personal care products, and they have attracted increasing attention during the last years because they have negative effects to human and ecological health. So there are still several challenges for the development of the technology, for the scale-up and industrial implementation. As Javier and José Antonio said before, the modeling is really important in order to avoid these kind of challenges, but also there are more challenges. In the case of the photocatalysis, as you know, you need an adequate source of light in order to excite the photocatalyst and generate the hydroxyl radicals, which are responsible of the removal of the pollutant. And as you know, the most sustainable option is to use the sun. However, it has some disadvantages, like heterogeneous distribution. I come from the north of Spain, so we don't have as much sun as you have here in Alcoy, so that's one disadvantage in our case. Also, sometimes large areas are required, and it is a discontinuous technology. Moreover, the most used photocatalyst, the titanium dioxide, is only excited for wavelengths before 387 nanometers, that is the UV region, and since less than 5% of the sun's light that is reaching the Earth's surface is within this range, sometimes it is required to use artificial lamps such as mercury lamps or xenon lamps. What happens is that they have a high energy intake and they have a low efficiency converting electricity into light. Moreover, they have short for useful life. But the most important part is that the energy optimization is required. That's why the LED, light-emitting diodes, appear as a sustainable solution, like a good source of light. They have less toxic nature, high efficiency transforming energy into light, also stability, longer useful life, they are compact, and the price at the beginning was more expensive, but it has decreased a lot in the last years. Moreover, they can emit in a specific wavelength. So as I told you, we have experience in the design of these kind of reactors, and what is important is that LED provides you flexibility. So you can adapt the LED to your system. You can select external radiation, internal radiation. You can work with a lamp that can include UV LED, visible LED, both kind of them. Well, that's just an example. You can have several kind of lens in the same lamp. You can also work in different radiation intensity regimens. And obviously, you can have an adequate source of light for different reactors, for SCTRs, annular, boxes, cells, plates. So that's the more important part of working with this kind of source of light. Also, you can work with different operation modes, obviously. But the best way of seeing this is in different examples. Here we can see a reactor with external radiation. As you can see, there are several LED strips surrounding an SCTR reactor. In this case, you can switch on or switch off all the LED strip by pairs. But we don't recommend this kind of photoreactors because the distance between the LED and the reaction media is higher. And as you know, the radiation intensity decreases with the square root of the distance. So we recommend to our clients to try another kind of reactors. But anyway, we can build this kind of reactors. They have been used. Here we have an immersion lamp LED photoreactor. These kind of reactors are very useful for some researchers who want to compare the results with the traditional mercury lamps. As Javier said, each reactor has a different geometry, so it's quite complicated try to compare it without the modeling that they explained, but it's helpful if they are similar. So in this case, we have a lamp that includes both kind of LED, UV and visible, and you can regulate the radiation intensity of the lamp in order to optimize the energy consumption. So it's really useful in order to save treatment cost. Well, something really important with LED reactors that I want to point out is that you have to control the temperature of the LED in a proper manner. So you always have to include an adequate refrigeration system. In this case, the refrigeration is done by forced air conversion, and it's automatically controlling a PLC. So if the temperature of the LED increases, the PLC sends the order to the fan, and it takes off more air. It's very important to keep a constant temperature because you preserve the long useful life of the LED, which is one of the main advantages. And also because in that way they emit in a constant way. Here we have more examples, like this one is located in a research institute in Murcia in Spain. And this one is located at the Chemical Institute at Sarriá, also in Spain. Another kind of design is the annular photoreactor. So in this case, you have an inner tube where you have located your LED strips. Usually there are 2 or 4 LED strips. Obviously, it's better to have 4 LED strips in order to have a better radiation distribution. And well, in this case, you will need a more complex system because you're going to need a feeding tank for the dark phase of the photocatalyst absorption, a recirculation pump, and then you can add anything else you want, like well, measurement for pH, temperature, it depends on what you need, and also a system for the photocatalyst recovery. This one is located at the University of Lappeenranta in Finland, but we can find several examples of this kind of photoreactors. This last one is a little bit bigger, it's for a pre-pilot scale, but I think that you will find this one more interesting. This one is located in a wastewater treatment plant in Murcia. It's a pilot plant scale, and it's a good example of what LED can offer to different systems, because working with these systems, we are working with a CPC during the day, but in the night we are using LED, two LED annular photoreactors. So even if you don't have enough radiation intensity during the day, you have a radiometer. So the system will automatically switch to the LED photoreactors. So with this working procedure, you have the energy consumption optimized. And well, it is really important to point out that this system can work 24/7, which is something really important in the photocatalysis. And we have developed a system even for working with suspended photocatalyst in a continuous way, so it's really useful. Something that I would like to show you before moving to the results is that you can also combine the photocatalytic process with other advanced oxidation process in order to optimize the energy. So here you can see an example of a LED annular photoreactor, an electrochemical cell. So you can work with a combination of them, or you can compare them by separately. Obviously, the ones that I show you are just some examples. With the LED, you can design cells, you can design different kind of lamps, and we are currently working in the improvement of the light distribution within the reactors. But there are a lot of examples. It will take me a lot of time to show all of them. So as a result, I want to show you a comparison between the energy consumption in one annular LED reactor and in a traditional mercury lamp. This comparison was performed for the removal of the surfactant sodium dodemethyl sulfonate, SDVS. And in the case of the mercury lamp, it is emitting between 200 and 600 nanometers with a fixed electrical power of 150 watts. While in the case of the LED photoreactor, the lamp is emitting between 365 and 370 nanometers with a electrical power varying from 1 to 100 watts. So in the case of the LED photoreactor, you can modify the radiation intensity, and obviously the electrical consumption will change. Well, for the experiments, the photocatalyst used was the titanium dioxide P25, the most used one, the commercial one from Evonik Industries, at a fixed concentration of 1 gram per liter. And the initial amount of SDVs was 50 milligrams per liter. So the titanium dioxide was added to a synthetic solution of SDVs, and it was kept in the dark until reaching the absorption equilibrium. Then the photocatalysis experiments were started, and several samples were taken at different times. And the evolution of the SDVs was followed through spectrophotometry. Well, besides following the removal of the pollutant, the amount of the hydroxyl radical generated was also estimated for different radiation intensities. As you can see, there is a linear relationship for all the radiation intensity, and obviously the highest amount of hydroxyl radicals was attained with the highest radiation intensity, that was 27.5 milliwatts per square centimeter. And the highest removal of SDVs after 8 hours was about 99%, working also with the highest radiation intensity. But what I want to show you here is the electrical evaluation, the energy evaluation that we perform here. With this aim, we use the parameter electrical energy per order, the EEO, which estimates the amount of electricity that is required to remove the contaminant by 1 order of magnitude. That is a 90% in a fixed volume of wastewater. So we want to have the smallest possible value of the EEO because it indicates that your system is quite efficient. So in this case, the optimum conditions were found working at 322 milliwatts per square centimeter. In order to obtain the EEO, all the pollutant removal results were fit to a pseudo-first kinetic order, but the EEO was about a 48 kilowatts hour per cubic meter an order. Well, in this kind of photoreactors, you can also check in which reaction rate regimen you are working at. So as you know, there are 3 regimens regarding the intensity of the light for the reaction rate. For low intensities, there is a linear relationship between the reaction rate and intensity. For higher ones, there is the reaction rate depends on the square root on the intensity of the light. And if you keep increasing the intensity of the light, the reaction rate is no longer affected by it. So we developed a kinetic model for the hydroxyl radicals generation using the estimation tool solver. And it allows us to check that working with this LED photoreactor, you can work in the 3 regimens, as you can see here. But what is more important, it allows you to estimate the minimum radiation intensity that allows you to obtain the highest generation rate for the hydroxyl radicals. Well, as you can see in this graph, the model was well fit to the experimental data. And what happened if we compare the result obtained at the LED reactor to a traditional lamp? Well, as you can see here, the kinetics of the mercury lamp were much faster. You can see here also with the kinetic constant. However, if you analyze the EO, it shows you that in the case of the LED reactor, it's almost 30-fold smaller than in the case of the mercury lamp. So apparently, first when you see these results, you will choose the mercury lamp because it's faster. But if you study both systems from a kinetic and energy coupled point of view, you will choose the LED because it's most efficient. It is really important to keep working in this kind of designs. The LED having been developed in the last year, they are improving a lot. The results that I show you were obtained with what we call a first generation LED. But right now we are using LED with higher radiation intensity and lower electricity consumption, so we could enhance the performance of the equipment. We are right now participating in a project called LED for Future for the new generation of UV-lit photocatalytic reactors for the removal of emerging contaminants. And we are trying to improve the distribution of the light within the reactors, and we are trying to improve the designs that we have already implemented for our clients. So I will conclude with some ideas. As I showed you, the photocatalysis has shown its technical viability for the removal of emerging contaminants. However, some challenges has to be overcome in order to implement it in an industrial way. One of the main challenges is the energy optimization, but as I showed you, the use of LED appears as a sustainable source of light. But however, they are quite new, so we have to still work in their designs and try to improve their performance. Well, I would like to thank you for your attention. If you have any questions, I will try to answer them. And before I forget, here you have my contact in case you need further information about the designs of the LED reactors. And I also brought some USB for the students that are interested in LED reactors, so you can collect them afterwards if you want.
Okay, thank you, Sara, for your nice and interesting presentation.